Hi, welcome to the second unit here in AP Physics 1. This is the unit on dynamics. So these are going to be Newton's laws of motion. But we're going to take a little bit of time to get there because there are some things that we need to handle first. With the first thing being here in this topic 2.1 is going to be systems and center of mass. All right. So systems are very important here in physics because it helps us identify, what things are happening or where things are happening. It allows us to make some of these problems that we're going to encounter very easy versus, if we have a single system versus two separate systems. So a system, you think about it, is an object or simply a collection of objects. So what we say is that objects are treated to have no internal structure. So if it's like a block, that's just a simple object, right? A collection of objects would be what you kind of see here to the right. These are what are called Atwood machines. And so you have two masses hanging off these pulleys. And so those are what we call, collection of objects. And so what happens is the system will have a boundary, and that boundary defines what is inside and what is outside. So to make these problems easier, right, it's like we take this and say this is our boundary. So anything inside that circle is what we're going to handle, and anything outside that circle now becomes external. So like this would be the system here. Again, anything inside that circle, that's what we're going to focus on. Anything outside becomes external, and that's what's causing the changes in motion. So systems will exchange energy, matter, or both with the surroundings. And so what happens is if we say it's an open system, that means there's going to be a exchange of matter and energy or energy, right? So it's like heat, right? So that's why you do heat experiments in like styrofoam. Or you try to minimize the heat loss. A closed system means that nothing can exchange right inside or outside. Now, for us really to make these problems easier, closed systems are the important thing. So you'll see a lot. We'll say for a system with no net external force, or it'll say for closed systems this is true, this is true. Okay. Now, a system can be in equilibrium, meaning it's not going to change over time. And so dynamic equilibrium means that the system will change, but will return to its state of equilibrium over time. So pendulums, right, really deal with this. Another way to think about dynamic equilibrium is that it's going to be moving in a way, but it's not going to be accelerated. Okay, so what happens is equilibrium means, right, that your acceleration equals zero. Okay, and you have two ways that could happen. Either the system is not moving or it's moving with a constant velocity. So that's a little preview of Newton's first law. All right, now, center of mass is something that's going to be taught a little bit earlier here in the new breakdown for AP Physics 1. This used to be handled in the linear momentum unit, but the center of mass of a system is a point that represents the average position, right, of all matter in the system. So it's like if you could put a dot, right, on what moves versus what doesn't move, okay, or, what is actually causing the motion, that's going to be your center of mass. And this is a famous picture with the hammer, but what you see is along the way, all this kind of line in the middle is all being kind of twisted around. Sorry, the red doesn't show up on red, right? So everything is going to move around that center of mass of the hammer. And you can see, we'll do a calculation here in a minute, but it's kind of just like where everything can be situated. Now, to find the center of mass, you're going to need to know two things. You're going to need the position of each component of the system, and you're also going to need to know the mass. So to find the location, and we're going to write it with a general, right? So we're going to say X center of mass is going to be equal to the sum of MI over the sum of MI. Now, this sum of MI on the denominator, right, that's just total mass. So even if a mass has a position of 0, you still have to add it to your total mass because your top part would be equal to, for that particular component, would be equal to 0. Now, you can easily, I know I wrote this with X, but this can easily be replaced with Y or Z, right? Those are the three. So you can do it two-dimensionally, right, with X and I. You can do it three-dimensionally with X, Y, and Z. Okay. Now, at the mass, so if it's, and this is important, right? If the problem says uniform distribution, right, it's going to be right in the middle. Okay. The only time it would potentially be like, let's say, a baseball bat, right, where more of the mass is towards the barrel of the bat versus the handle of the bat. Now, a common question they like to ask is when you have a person walking on a boat, where is the center of mass going to be located? Or, as you can see here, this one here, the person is going to walk in this direction. But something to note is the location of the center of mass does not change. Okay, the person where the boat is going to change, but the physical location of the center of mass will not change. You can also determine the velocity of the center of mass. So VCM equals the sum of MI/VI divided by the sum of MI. So again, so you get M times V up top for each component, and then you have the total mass in the denominator. And then you can also do the same thing with acceleration. So ACM equals the sum of MI/AI over the sum of MI. Okay, and so remember in each case that MI, the sum of MI in the denominator, that's total mass. Sometimes you'll see it written as like capital M or M sub T. Okay, so let's do a couple examples, of which one of the examples will be the boat problem. So here we have 3 people standing, okay, and part A says determine where the center of mass is, assuming that this is our X equals 0 position. And then we're going to have like some running. So in the second question, the 82 kilogram person is going to move to the right. And then the last one, the 70 kilogram person is going to move to the left. And so we have to find and B and C, we have to find the velocity. All right, so part A is very simple. So we're going to find the X position of the center of mass. So we're going to do MI/XI over sum of MI. And so I always like to write in, even if the person is at 0, just so you know, remember it for the denominator calculation. And you have to be careful. Yes, the 82 kilogram person is 6 meters away from the 0 point because they're 2 meters away, or they're 4 meters away from the 60 kilogram person, but the 60 kilogram person is 2 meters away from X equals 0. And so now you add up the masses. And what you find is that the center of mass for this system, not centimeters, it's in meters. So it's at 2.9 meters. So it's roughly in this area, okay? And you can see it is going to be a little bit skewed towards that 82 kilogram person, right? Because it's going to be skewed towards the larger, person in this case. All right, now in part B, what we have is the 82 kilogram person is going to run to the right, right? Everybody else is going to remain the same. We're going to find the velocity of the center mass. So we're going to do the sum of MI/VI over total mass. And you do have to account for the direction. So 70 kilogram person is not moving. The 60 kilogram person is not moving also. And then it's the 82 kilogram person who's moving in the positive direction. Again, divide everything by total mass. And we find that the center mass will have a velocity of positive 1.16 meters per second. All right, in part C, they want to now do what happens when both of them are not moving, right? And so the 70 kilogram person, again, not moving. The 60 kilogram person is now going to move to the left, right, at 6 meters per second. And the 82 kilogram person is still going to run there 3 meters per second to the right. And we have total mass. And you're going to find that the velocity of the center mass in this scenario is going to be negative 0.82 meters per second. So you can see, even though that's a lighter person traveling to the right or to the left, because their speed is faster, they're going to create more of an effect on that velocity of the center of mass. All right, so let's look at the boat question. Here the boat question. So you got a 90 kilogram boat is floating in water, 30 kilogram person is on it. They're going to walk from the stern to the bow. So the stern is the front of the boat, bow is the back of the boat. So what they're going to do is they're going to walk like in this direction. And it tells us the boat has a length of 3 meters. And the question is, how far does the boat move, right? So one thing to remember, I put V, it should be X. Oh, and then I hit the wrong button. I don't know why I can't go further. There we go. Oh, now I gotta go back. So the position, remember the before position of the center of mass is going to equal the after, which that means my delta, my change in center mass is going to be 0. And that's going to be very important. Okay. So we know that the center of mass, right, is going to be located at m1 x1 plus m2 x2 over total mass. Now, remember, this is the system center of mass, not the boat, okay? But we know that the change in the center of mass, right, is going to be equal to the change in, right, x1 plus the change in x2, right, over m1 plus m2. But we know that that is going to equal 0, which means we just have to do a little bit of algebra. Because if I do my first bit of algebra, that part's going to cancel out, and it's just going to equal 0. And so we know that this is 3 meters, right? And then we need to figure out where x is. So that the person's is going to be 3 minus x, and then the boat is going to be negative x, right? Because that's the location we're looking for. That's all going to equal 0. So I have 3m1 minus 3x plus, minus mx, m2x, okay, equals 0. And I do a little bit of, I can, do some math here, and that becomes, 3m1 becomes, m minus m2 plus 3x. I seem to have kind of butchered this a little bit. Let's do this. Let's bring the m1x over, or m2x. We get 3m1 minus 3x, okay? And so now I bring the plus 3x over, so I get m2 plus 3. Sorry, I apologize. I seem to have lost a 3 somewhere in here in my notes. I forgot. I lost the m2 also. Oh, it's right here. So this would be m1x. That's why. Okay. Fixed. All fixed. So, come back in here. Didn't distribute properly. That's what happened. So I get 3m1 minus m1x minus m2x equals 0. So then I have 3m1 equals m1 plus m2x. There we go. And so x, which is how far the boat moves, is 3m1 over m1 plus m2. m1 is our person, m2 is our boat. And so we end up with 3 times 30 over 120, which is equal to 0.75 meters. And I do apologize for the confusion. When I distributed the M1, I didn't distribute properly. Okay, so that's the boat question. I do like that one. They'll do this question in multiple choice. And so just be aware of that. But remember, as long as there's nothing from the outside, the change in the position of the center of mass is always going to be 0.